The James Webb Space Telescope has just shown us something that nobody expected. Something so strange, so unsettling, that it is forcing scientists to question everything they thought they knew about the universe. And what it revealed is this: the universe is not just bigger than we imagined. It is older, stranger, and more packed with galaxies than any model ever predicted. In fact, what Webb is showing us right now might just break physics as we know it. Before we dive into the infinite, please like this video and subscribe to the channel if you enjoy learning about the mysteries of space. Your support helps us keep exploring the cosmos together. Now, picture this. You are standing on a beach at night. The sand beneath your feet stretches out in every direction. Each grain is tiny, almost too small to see. And yet, there are more grains of sand on this beach than you could ever count in a lifetime. Now imagine every beach on Earth, every desert, every sandbox. Scientists once believed that the number of stars in the observable universe was roughly equal to all those grains of sand combined. That number is somewhere around 10 to the power of 22. Written out, that is a 1 followed by 22 zeros. It is a number so large that your brain cannot truly picture it. But here is the thing. The James Webb Space Telescope is now suggesting that even that number might be too small. Way too small. Because what Webb is finding out there, in the deepest reaches of space, is changing the math. The telescope has spotted galaxies that should not exist. Stars that formed too early. Light from a time when the universe was supposed to be dark and empty. And all of this points to one incredible conclusion. The universe we can see, the part we call the observable universe, might just be the tip of a much, much larger iceberg. To understand why this matters, we first need to understand what the James Webb Space Telescope actually is and why it is so special. Webb is not like any telescope you have ever seen. It is not a tube with a glass lens that you point at the sky. Instead, it is a giant golden mirror floating in space, about 1 million miles from Earth. That mirror is made up of 18 smaller mirrors, all coated in a thin layer of gold. Together, they form a surface about 21 feet across. That is nearly 3 times wider than the mirror on the old Hubble Space Telescope. But size is only part of what makes Webb so powerful. The real magic is in what kind of light it can see. You and I can see visible light. The colors of the rainbow: red, orange, yellow, green, blue, and violet. But visible light is just a tiny slice of all the light that exists in the universe. There is also ultraviolet light, which gives you sunburns. There are X-rays, which doctors use to see your bones. And there is infrared light, which you feel as heat. Webb was built to see infrared light. And that might sound boring at first. Why would you want to look at heat instead of colorful stars and galaxies? The answer has to do with something called redshift. And redshift is one of the most important ideas in all of astronomy. Imagine you are standing next to a train track. A train is coming toward you, blowing its horn. As it gets closer, the sound of the horn seems higher in pitch. Then, as the train passes and moves away, the sound drops to a lower pitch. This happens because the sound waves are being squeezed together as the train approaches and stretched out as it moves away. This is called the Doppler effect, and it works for light too. When a galaxy is moving away from us, the light it gives off gets stretched out. The waves become longer, and longer wavelengths of light are redder. So we say the light has been redshifted. Now here is the key part. The universe is expanding. Every galaxy is moving away from every other galaxy. And the farther away a galaxy is, the faster it is moving away from us. This means the light from very distant galaxies is stretched so much that it shifts right out of the visible spectrum and into the infrared. This is why Hubble had trouble seeing the oldest galaxies. Hubble was mostly designed to see visible light. It could see some infrared, but not the deep, long wavelength infrared that comes from the most ancient parts of the universe. Webb, on the other hand, was built from the ground up to see exactly that kind of light. It can peer through cosmic dust. It can detect the faintest glow from objects that are billions of years old. It can see the universe as it was just a few 100 million years after the Big Bang. And what it is seeing is stunning. Let us talk about the Big Bang for a moment. About 13.8 billion years ago, everything in the universe was compressed into an unimaginably small, hot, dense point. Then, in a fraction of a second, it began to expand. Energy turned into matter. Space itself stretched outward. For the first few 100,000 years, the universe was so hot and thick that light could not travel freely. It was like trying to see through fog, except the fog was made of superheated particles. Then something changed. The universe cooled down enough for atoms to form. Protons grabbed onto electrons and became hydrogen. Some became helium. And suddenly, light could move. This moment is called recombination, and the light released back then is still traveling through space today. We call it the cosmic microwave background, and it is the oldest light we can see. It is like an echo of the Big Bang itself. But here is the mystery. After recombination, the universe entered a period called the cosmic dark ages. There were no stars yet, no galaxies, just clouds of hydrogen and helium floating in the blackness. The universe was quiet and dark. Scientists believed that it took hundreds of millions of years for gravity to slowly pull those clouds together, forming the first stars and eventually the first galaxies. According to the old models, the first galaxies should have been small and messy. They should have been faint. They should have taken a long time to grow. It was like expecting a seedling to slowly become a tree over thousands of years. But Webb is showing us something completely different. In some of its very first images, Webb spotted galaxies that existed just 500 to 700 million years after the Big Bang. That might sound like a long time, but in cosmic terms, it is almost nothing. The universe is 13.8 billion years old. 500 million years is barely 4% of that. It is like looking at a 90-year-old person and finding out they were fully grown by age 3. And these early galaxies are not small and messy. Some of them are huge, massive, packed with stars. They look like galaxies that should have taken billions of years to form. Scientists were so shocked by these findings that they started calling them universe breakers. Because if these galaxies are real, and if they really are as old and massive as they appear, then something is very wrong with our models. One astronomer, a man named Ivo Laber, was among the first to spot these strange objects in the Webb data. He was working late one night, scrolling through images, when he noticed a small red dot. Red dots in Webb images often mean very distant objects because of that redshift that we talked about. So he ran the numbers, and what the computer told him made him nearly choke on his coffee. The object was about 13.1 billion light-years away, and it contained the mass of about 100 billion stars. That is roughly the same as our entire Milky Way galaxy. But this object existed when the universe was only about 700 million years old. It should have been impossible. The next day, Laber and his team found 5 more objects just like it. "We just discovered the impossible," Laber later said. "Impossibly early, impossibly massive galaxies." Now, you might be wondering, could there be a mistake? Could the telescope be wrong? That is a fair question, and scientists are asking it too. There are a few ways the data could be misleading. For one thing, some of these objects might not be galaxies at all. They could be quasars, which are supermassive black holes that are eating so much matter that they shine brighter than entire galaxies. If that is the case, then the light is not coming from billions of stars. It is coming from one incredibly powerful source. Another possibility is that the distances are wrong. Webb measures distance using redshift, and there are some cases where the numbers can be tricky. A galaxy might look very redshifted, but actually be closer than it appears if there is something unusual about its light. Scientists need to take more detailed measurements, called spectra, to confirm exactly how far away these objects are. But here is the thing. Even if some of these universe breakers turn out to be something else, there are still too many of them. Webb is finding far more bright, massive galaxies in the early universe than anyone expected. And that alone is a problem, because our best models of the universe say that the early cosmos should have been mostly empty. There should not have been enough time or matter to build these giant structures. So what is going on? One idea is that stars formed much faster in the early universe than we thought. Maybe the first stars were not like the stars we see today. Theory suggests that the very first stars, called population 3 stars, could have been absolute monsters. We are talking about stars that were 30 to 300 times the mass of our Sun, stars that burned millions of times brighter. These stellar giants would have lived fast and died young, exploding as supernovae after just a few million years. If there were lots of these massive stars in the early universe, they could have pumped out enormous amounts of light. That would make early galaxies appear much brighter and more developed than they actually were. It is like putting a spotlight on a small stage and making it look like a Broadway show. Another possibility is even more exciting. Some scientists think the early universe might have had more dark matter than we realized. Dark matter is a mysterious substance that does not give off light or interact with normal matter in any obvious way. We know it exists because we can see its gravitational effects on galaxies and clusters, but we have never detected it directly. If there was extra dark matter in the early universe, it could have helped pull matter together faster. Think of it like adding extra glue to a construction project. Things would stick together sooner and build up quicker. But there is a third possibility that is even stranger. What if our entire model of cosmology is wrong? What if there is something about the laws of physics, the expansion of the universe, or the nature of space and time that we have misunderstood? This brings us to one of the biggest mysteries in modern science. It is called the Hubble tension, and it has been driving astronomers crazy for over a decade. The Hubble tension is not about galaxies being too big or too early. It is about the universe expanding at the wrong speed. Here is how it works. Scientists have two main ways of measuring how fast the universe is expanding. The first way is to look at objects in the nearby universe, like certain types of exploding stars called supernovae. By measuring how bright these explosions are and how fast they are moving away from us, we can calculate the expansion rate. This method gives a number around 73 kilometers per second per megaparsec. That sounds complicated, but it basically means that for every million parsecs you travel away from Earth, space is stretching at 73 kilometers per second faster. The second way to measure expansion is to look at the cosmic microwave background, that ancient light from the Big Bang. By studying tiny ripples and patterns in that light, scientists can figure out what the early universe was like. They can then use computer models to predict how fast the universe should be expanding today. This method gives a lower number, around 67 kilometers per second per megaparsec. The difference between 73 and 67 might not seem like a lot, but in the world of precision cosmology, it is huge. The two measurements should match. They do not. And despite years of checking and double-checking, the gap will not go away. Now here's where Webb comes in. Scientists hoped that Webb's sharp vision would solve the Hubble tension once and for all. Maybe Hubble had been making small errors in its measurements. Maybe there was dust or crowding that was throwing off the numbers. Webb could see much more clearly, so it should be able to sort things out. But Webb made things worse, or better, depending on how you look at it. In late 2024, a team led by Nobel Prize winner Adam Rees used Webb to study the same objects that Hubble had measured. They found that Hubble's numbers were basically correct. Webb confirmed that the nearby universe is expanding faster than the distant universe says it should be, so the Hubble tension is real. It is not a mistake, and that means something is missing from our understanding of the cosmos. Some scientists think there might be a new type of energy or matter that gave the universe a boost shortly after the Big Bang. They call it early dark energy. It would have pushed the universe to expand faster in its youth, which would explain why the expansion rate looks different depending on how you measure it. Others think the answer might involve new physics we have not discovered yet. Maybe gravity works differently on very large scales. Maybe there are extra dimensions we cannot see. Maybe the fabric of space-time has properties we do not understand. Whatever the answer is, it almost certainly means the universe is stranger than we thought, and Webb is helping us see just how strange it might be. Let us zoom out for a moment and talk about scale, because when we say the universe is big, we really mean it. The observable universe, the part we can see, has a diameter of about 93 billion light-years. Now wait a second, you might say. If the universe is only 13.8 billion years old, how can it be 93 billion light-years across? Should it not be about 27 billion, since light has only had that much time to travel? This is where things get trippy. Remember, the universe is expanding, and it has been expanding since the Big Bang. So while light from the most distant objects has been traveling toward us for billions of years, the space between us and those objects has been stretching the whole time. By the time the light reaches us, the objects that sent it are much, much farther away than they were when the light left. Think of it like this. Imagine you are on one end of a really long rubber band, and your friend is on the other end. Your friend sends a marble rolling toward you, but while the marble is rolling, someone starts stretching the rubber band. By the time the marble reaches you, your friend is much farther away than when they sent it. The marble traveled a certain distance, but the rubber band itself grew. That is what is happening with light in our expanding universe. The light from the most distant objects we can see was emitted about 13.8 billion years ago, but those objects are now about 46 billion light-years away. Double that for both directions, and you get a universe roughly 93 billion light-years across. But here is the kicker. That is just the observable universe. The part we can see. There is almost certainly more universe beyond that. We just cannot see it, because the light has not had time to reach us yet. And because the universe is expanding faster than light can travel, some of that distant universe will never be visible to us, no matter how long we wait. How much more is out there? We do not know. Some scientists think the total universe could be many times larger than the part we can see. Others think it might be infinite, an endless ocean of galaxies stretching out forever in every direction. Webb is helping us understand this by showing us just how packed the observable universe really is. Before Webb, scientists estimated there were about 200 billion galaxies in the observable universe. That was already a mind-boggling number. But Webb's deep field images are revealing that there might be even more. Some estimates now suggest 2 trillion galaxies or more. That is 10 times what we thought before. And if the density of galaxies in the parts Webb can see is typical of the whole universe, then the total number of galaxies out there, including the ones we will never see, could be almost beyond counting. Each of those galaxies contains hundreds of billions of stars. Each star might have planets, and each planet might have moons. The sheer number of worlds in the cosmos is staggering. This is the true scale that Webb is revealing. Not just bigger distances, but more stuff, more galaxies, more stars, more chances for something interesting to happen, more possibilities for life. But to really appreciate what Webb is showing us, we need to go back in time. Way back to when the first lights in the universe switched on. After the Big Bang, the universe was a hot, glowing soup of particles. Protons, neutrons, and electrons swirled around in a cosmic storm of energy. For about 380,000 years, this chaos continued. The universe was so hot and dense that light could not escape. Photons, the particles of light, kept bumping into electrons and getting scattered in random directions. It was like trying to see through a wall of fire. Then something beautiful happened. The universe cooled enough for electrons to settle down and attach to protons. Hydrogen atoms formed. And suddenly, light was free to travel. This moment is called the surface of last scattering, and the light that was released has been traveling through space ever since. We see it today as the cosmic microwave background, a faint glow that fills the entire sky. It is the oldest light in the universe, and it tells us what things looked like when the cosmos was just a baby. But after this burst of light, the universe went dark. Not because there was nothing there, but because there were no sources of light, no stars, no galaxies, just vast clouds of hydrogen and helium drifting through the blackness. Scientists call this period the cosmic dark ages, and it lasted for hundreds of millions of years. Imagine the loneliest, emptiest night you can think of. No moon, no streetlights, no stars, just pure, unbroken darkness stretching in every direction. That was the universe during the Dark Ages. It was waiting for something to happen, waiting for the first lights to turn on. Deep, within those clouds of gas, gravity was slowly doing its work. Hydrogen atoms drifted closer to each other, pulled together by their own weight. Over millions of years, these clumps grew denser and heavier. The gas at the center got hotter and hotter as it compressed. And then, at some point, something remarkable occurred. The temperature and pressure at the heart of one of these clumps became so extreme that hydrogen atoms began to fuse together. This is nuclear fusion, the process that powers every star in the universe. When hydrogen atoms fuse, they release enormous amounts of energy. Light, heat. The first star had been born. We do not know exactly when the first star ignited. It might have been 100 million years after the Big Bang, or maybe 200 million. But whenever it happened, it was one of the most important moments in cosmic history. For the first time since the Big Bang, there was a source of light in the universe. The Dark Ages were ending. These first stars were probably nothing like the sun. They were giants, monsters. Some of them might have been 300 times the mass of our sun, blazing with a fury we can barely imagine. They burned through their fuel in just a few million years and then exploded in spectacular supernovae. When they died, they scattered heavy elements, metals and dust into the surrounding space. These elements would later become the building blocks of planets and, eventually, life. The light from these early stars did more than just brighten the darkness. It transformed the universe itself. The energetic ultraviolet radiation from these massive stars began to rip apart the hydrogen atoms that filled space. It knocked electrons loose from protons, turning neutral hydrogen back into a hot plasma. This process is called Reionization, and it was like a second Big Bang in slow motion. Reionization did not happen all at once. It started in pockets around the brightest stars and galaxies. These pockets of ionized gas grew larger and larger, like bubbles in a pot of boiling water. Eventually, the bubbles merged, and the entire universe became transparent to light once again. Scientists believe reionization was mostly complete by about 1 billion years after the Big Bang. Webb is now giving us our first clear look at this incredible era. And what it is finding is astonishing. In early 2025, a team of astronomers announced they had detected light from a galaxy called Jade's GS 31. This galaxy existed just 330 million years after the Big Bang. That is less than 3% of the universe's current age. And this galaxy was already doing something amazing. It was blowing a bubble of ionized gas into the surrounding darkness. This is the earliest evidence of reionization we have ever found. It is like finding a tiny candle in a dark room and realizing that candle was the first one ever lit. But Jade's GSZ 13.1 is not alone. Webb has found hundreds of galaxies from this early era, and many of them are surprisingly bright, surprisingly active. They were forming stars at a furious rate, pumping out torrents of ultraviolet light. These galaxies were the architects of the universe we see today. They cleared the fog. They lit the way. The record for the most distant galaxy keeps getting broken. In May 2024, Webb confirmed a galaxy called Jade's GS Z14-0, seen as it was just 290 million years after the Big Bang. This galaxy has a redshift of about 14, which is a measure of how much its light has been stretched by the expansion of the universe. The higher the redshift, the more distant and ancient the object. Before Webb, the most distant confirmed galaxy had a redshift of about 11. Webb has shattered that record and keeps pushing further back. Scientists now believe Webb might eventually find galaxies from as early as 200 million years after the Big Bang, or maybe even earlier. Each of these discoveries is like finding a new page in the universe's baby book. We are seeing what the cosmos looked like when it was just waking up, when the first structures were forming, when the raw materials of everything we see today were being assembled. But Webb is not just looking back in time. It is also looking outward at the incredible variety of objects that fill the universe. And one of the most exciting frontiers is the search for other worlds. Planets beyond our solar system are called exoplanets. Before the 1990s, we had never confirmed a single one. We suspected they existed, but we had no proof. Then in 1995, astronomers discovered the first exoplanet orbiting a sun-like star. Since then, we have found thousands more. Big planets, small planets, hot planets, cold planets, planets made of gas, planets made of rock. But finding an exoplanet is just the first step. The real question is whether any of these worlds could support life. And to answer that, we need to know what their atmospheres are like. Are they filled with poisonous gases? Do they have water? Is there oxygen? These are the clues that could tell us if a planet is habitable or even inhabited. This is incredibly hard to do. Exoplanets are small and faint compared to their host stars. Trying to study an exoplanet's atmosphere is like trying to see a firefly next to a searchlight from 1,000 miles away. But Webb was designed with exactly this challenge in mind. One of the most studied systems is TRAPPIST-1, a collection of 7 rocky planets orbiting a small, cool red dwarf star about 40 light-years from Earth. 3 of these planets orbit in the habitable zone, the region where temperatures might be just right for liquid water to exist. TRAPPIST-1e is especially interesting because it is roughly the same size and density as Earth, and it sits right in the middle of that sweet spot. Webb has been observing TRAPPIST-1e and its siblings for years now, trying to figure out if any of them have atmospheres. The results so far are a mix of tantalizing hints and frustrating challenges. For TRAPPIST-1b and c, the 2 innermost planets, Webb has found evidence that they are probably bare rocks. They receive so much radiation from their star that any atmosphere they once had has likely been stripped away. This is not surprising. Red dwarf stars are known to be violent in their youth, blasting their planets with powerful flares that can erode atmospheres over time. But TRAPPIST-1e is farther out, in a safer zone, and recent observations have found hints, just hints, that it might have a thin atmosphere. Nothing definitive yet, but the data suggests there could be something there. Maybe nitrogen, maybe traces of other gases. Scientists are being very careful not to jump to conclusions. They know how easy it is to be fooled by noise in the data, or by signals from the star itself. The challenge is that TRAPPIST-1 is an active star. It flares frequently, and those flares create signals in the data that can mimic or mask the signatures of an exoplanet atmosphere. Sorting out what is coming from the planet and what is coming from the star is like trying to hear a whisper at a rock concert. To solve this problem, astronomers are using a clever trick. They observe TRAPPIST-1e at the same time as TRAPPIST-1b, which is known to have no atmosphere. By comparing the 2 signals, they can subtract out the star's contribution and hopefully see what TRAPPIST-1e alone is doing. This work is ongoing. It will take many more observations and a lot of careful analysis before we can say for sure whether TRAPPIST-1e has an atmosphere. But the fact that we are even asking this question is remarkable. A generation ago, we did not know if exoplanets existed. Now we are studying the air on worlds 40 light-years away. And TRAPPIST-1 is just one system. Webb is also studying dozens of other exoplanets, each with its own mysteries. It has detected carbon dioxide and water vapor in the atmospheres of gas giants. It has found evidence of clouds and weather on distant worlds. Every observation adds to our understanding of how planets form, evolve, and maybe, just maybe, develop the conditions for life. But let us return to the big picture. Because when we talk about the scale of the universe, we cannot ignore the 2 largest players in the cosmic game: dark matter and dark energy. You have probably heard these terms before. They sound mysterious, and they are. Dark matter and dark energy together make up about 96% of the universe. Everything you can see, every star, every galaxy, every planet, every person, every atom, all of that is just 4% of the total. The rest is dark. Let us start with dark matter. We call it dark because it does not give off light. It does not absorb light. It does not interact with light in any way we can detect. So how do we know it exists? The answer is gravity. We can see the effects of dark matter even though we cannot see dark matter itself. Imagine you are watching a puppet show. The puppets are dancing around on stage, moving in complex patterns, but you cannot see the strings. You cannot see the puppeteer. All you can see are the puppets. You would still be able to figure out that something is controlling them, because their movements would not make sense otherwise. That is what dark matter is like. We see galaxies spinning in ways that should tear them apart. Stars on the outer edges of galaxies are moving so fast that they should fly off into space. But they do not. Something is holding them in place. An invisible hand. That hand is dark matter. We also see dark matter bending light. This is called gravitational lensing. When light from a distant galaxy passes near a clump of dark matter, the gravity bends the light like a lens. We see the background galaxy stretched and distorted, sometimes appearing as multiple images or long arcs. By studying these distortions, we can map where the dark matter is, even though we cannot see it directly. Webb is helping with this work. Its sharp vision and sensitivity to faint light make it ideal for studying gravitational lensing. By observing how light from the most distant galaxies is bent and warped, scientists are building maps of the dark matter that fills the universe. These maps show a cosmic web, a vast network of dark matter filaments that stretch across billions of light years. Galaxies and galaxy clusters are strung along these filaments like pearls on a necklace. This cosmic web is the skeleton of the universe. It is the framework on which everything else is built. Without dark matter, galaxies would not have formed. The universe would be a thin, featureless soup of gas. Dark matter is what pulled things together, what created the structure we see today. But as strange as dark matter is, dark energy is even stranger. In the 1990s, two teams of astronomers set out to measure how fast the universe was expanding and whether that expansion was slowing down. They expected to find that gravity was putting the brakes on expansion, gradually slowing it over time. Instead, they found the opposite. The expansion of the universe is speeding up. This was one of the most shocking discoveries in the history of science. It earned the researchers a Nobel Prize and sent theorists scrambling for an explanation. The name they gave to the mysterious force driving this acceleration is dark energy. We do not know what dark energy is. It could be a property of space itself, a kind of energy that permeates the vacuum. It could be a new force of nature. It could be something completely beyond our current understanding of physics. What we do know is that dark energy makes up about 68% of the universe, and its effects are enormous. As the universe expands, dark energy pushes it to expand faster. Over billions of years, this acceleration will transform the cosmos. In the far future, trillions of years from now, the expansion driven by dark energy will carry most galaxies beyond the visible horizon. They will move away so fast that their light will never reach us. Future. Astronomers, if there are any, will look out at a sky that appears mostly empty. The evidence for the Big Bang, for the cosmic web, for the history of the universe, will have faded from view. They will think they live in a small, lonely cosmos, with no idea of the vastness that once surrounded them. This is a sobering thought. We live in a special time, when the universe is still young enough for us to see its history written in the sky. Webb is helping us read that history before it fades away. And the history is getting stranger all the time. One of the biggest surprises from Webb has been the discovery of supermassive black holes in the early universe. Black holes are regions of space where gravity is so strong that nothing can escape, not even light. Supermassive black holes are the giants of this family. They contain millions or billions of times the mass of our Sun, and they sit at the centers of most large galaxies. We used to think supermassive black holes grew slowly over cosmic time. They would start small and gradually get bigger by eating stars and gas over billions of years. But Webb is finding supermassive black holes that existed when the universe was less than 1 billion years old. Some of them are absolutely enormous, containing hundreds of millions of solar masses. How did these black holes get so big so fast? This is one of the hottest questions in astronomy right now, and Webb keeps making it more puzzling. One possible explanation is that black holes in the early universe grew from different seeds than the ones we see today. Maybe the first black holes formed from the direct collapse of massive gas clouds, skipping the star phase entirely. These so-called direct collapse black holes could have started out much heavier than black holes formed from dying stars, giving them a head start on their growth. Another possibility is that early black holes grew much faster than we thought possible. There is a limit to how fast a black hole can eat material, called the Eddington limit. If a black hole tries to swallow too much too fast, the radiation pressure from the infalling matter pushes back and slows things down. But maybe the early universe had conditions that allowed black holes to exceed this limit, at least for short periods. Webb has also found a strange class of objects called little red dots. These are tiny, very red points of light that show up in deep field images. At first, scientists were not sure what they were. Some thought they might be distant galaxies. Others thought they might be quasars, those incredibly bright objects powered by feeding black holes. Now, after careful study, it seems like many little red dots are something in between. They are compact objects with active black holes at their centers, surrounded by thick veils of dust that redden their light. Some of them might represent a new stage of galaxy evolution that we have never seen before, a phase where the black hole is growing rapidly, possibly outpacing the growth of its host galaxy. One object, nicknamed Virgil, was recently revealed to be a cosmic shapeshifter. Invisible and ultraviolet light, it looks like an ordinary galaxy, but in infrared light, it transforms into a monster. The infrared data shows a supermassive black hole eating material at an extraordinary rate, hidden behind curtains of dust. The black hole in Virgil is much larger than it should be for a galaxy of that size and age. This finding challenges the idea that black holes and galaxies grow together in lockstep. It suggests that in some cases, black holes might get ahead of their galaxies. They might be the leaders, not the followers, in cosmic construction. Every time Webb looks deeper into the universe, it seems to find something that does not quite fit our models. Galaxies that are too big, black holes that are too heavy, structures that form too fast. It is like opening a history book and finding chapters that were never supposed to be there. And this brings us back to the central question of this video. What is the true scale of the universe? For a long time, we thought we had a pretty good handle on this. The observable universe is about 93 billion light-years across. It contains somewhere between 200 billion and 2 trillion galaxies. The total number of stars is around 10 to the power of 24, roughly the number of grains of sand on all of Earth's beaches. But Webb is suggesting these numbers might be too small. The telescope has found that the universe was making galaxies earlier and faster than we expected. This means there could be more galaxies out there than our old estimates predicted. If early galaxies were common, and if they kept forming throughout cosmic history, then the total population could be much higher. Some scientists now think the observable universe might contain tens of trillions of galaxies, not just 2 trillion. That would mean hundreds of times more stars, hundreds of times more planets, hundreds of times more chances for something interesting to be happening somewhere out there. And remember, this is just the observable universe, the part we can see. The total universe is almost certainly larger, possibly much larger, possibly infinite. If the theory of cosmic inflation is correct, then the universe expanded incredibly fast in the first fraction of a second after the Big Bang. During this inflation, space stretched by a factor of at least 10 to the power of 26, maybe much more. If inflation happened as the theory predicts, then the universe beyond what we can see could be unimaginably vast. Some estimates suggest it could contain more than 10 to the power of 100 stars. That number is so large it has no meaningful comparison. It is beyond counting, beyond imagining. We are specks on a pale blue dot, orbiting an average star, in an average galaxy, in a universe of trillions of galaxies. And that universe might just be an infinitely small bubble in something even larger. This is humbling. And it is also thrilling, because here is the thing. We figured this out. Tiny creatures on a small planet, using our brains and our tools, have managed to uncover the scale of reality. We built a telescope, launched it into space, and pointed it at the darkness. And the darkness told us its secrets. Webb is not done yet, not by a long shot. The telescope has only been operating for a few years, and it is designed to work for at least 20. Probably more. In the years ahead, it will keep pushing back the frontier. It will find older galaxies, stranger black holes, more distant worlds. It will test our theories and probably break a few more of them. The universe is not shy. It shows itself to those who look carefully, and Webb is looking very carefully indeed. Let us take a moment to truly appreciate what it means to look into deep space. Because when Webb points at a distant galaxy, it is not just looking far away. It is looking back in time. This is one of the strangest and most beautiful facts about the universe. Light travels fast, about 186,000 miles per second. That is fast enough to circle the Earth more than 7 times in a single second. But space is so big that even light takes a long time to cross it. When you look at the sun, you are seeing it as it was about 8 minutes ago. That is how long the light takes to travel from the sun to your eyes. The sun you see is always 8 minutes in the past. If the sun suddenly vanished, you would not know for 8 minutes. You would keep seeing it shining in the sky, blissfully unaware that it was already gone. Now stretch that idea across the cosmos. The nearest star to us, other than the sun, is Proxima Centauri. It is about 4 light years away. That means the light you see from Proxima Centauri left that star 4 years ago. You are looking at the past. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. When you look at Andromeda, you are seeing it as it was 2.5 million years ago. Back when our ancestors were just learning to walk upright on the plains of Africa, and the galaxies Webb is photographing are billions of light years away. Some of them are so distant that their light has been traveling for more than 13 billion years. When that light left those galaxies, the Earth did not exist. The sun had not formed. Even the Milky Way might have looked very different. This is why astronomy is often called the ultimate time machine. We cannot physically travel to the past, but we can see it. The farther we look, the farther back we go. Webb is the best time machine we have ever built. Its ability to see infrared light lets it peer deeper into cosmic history than any telescope before. And the images it sends back are windows into the ancient universe. But looking into the past comes with some strange side effects. One of them is time dilation. You may have heard of time dilation from science fiction movies about traveling close to the speed of light. When you move very fast, time slows down for you relative to someone standing still. This is a real effect predicted by Einstein's theory of relativity, and it has been confirmed many times by experiments. But there is another kind of time dilation that affects distant objects in an expanding universe. It is called cosmological time dilation, and it is caused by the stretching of space. When light travels through expanding space, it does not just get stretched into longer wavelengths. The expansion also affects how we perceive the passage of time for distant events. An explosion that takes 1 second in the distant universe will appear to take longer than 1 second when viewed from Earth. The expansion of space stretches out the duration of events, just like it stretches out the wavelength of light. This effect has been confirmed by studying distant supernovae. A supernova that happens in a nearby galaxy might take about 3 weeks to reach maximum brightness and fade away. But a similar supernova in a very distant galaxy, seen at high redshift, will appear to rise and fall over a longer period. The farther away it is, the more stretched out its timeline becomes. This might seem like a minor detail, but it is actually a powerful tool for astronomy. By measuring how much time dilation there is, scientists can confirm that the expansion of the universe is real and calculate its rate. It is another piece of evidence that our universe is getting bigger with every passing moment. Speaking of getting bigger, let us talk about what the expansion of the universe actually means. It is common to imagine the Big Bang as an explosion that happened in a specific place, sending debris flying outward through empty space. But that is not quite right. The Big Bang was not an explosion in space. It was an explosion of space. The universe did not expand into something. Space itself grew. This is a tricky concept to wrap your head around. In our everyday experience, things move through space. A ball flies through the air. A car drives down a road. But the expansion of the universe is different. It is the road itself getting longer. Imagine you are an ant crawling along a rubber band. Another ant is at the other end. If someone stretches the rubber band while you are both sitting still, you will find yourselves farther apart, even though neither of you moved. That is what is happening in the universe. Galaxies are not flying away from us through space. The space between us and them is stretching. This has some wild consequences. For one thing, very distant galaxies are receding from us faster than the speed of light. Yes, faster than light. This sounds impossible, but it is allowed by the laws of physics because the galaxies are not moving through space faster than light. Space itself is expanding, and there is no speed limit on the expansion of space. This means there are parts of the universe we will never be able to see, no matter how long we wait. The light from those regions is traveling toward us, but the space between us is expanding so fast that the light can never close the gap. It is like trying to run towards someone who is on a treadmill that keeps moving backward faster and faster. The boundary that separates the regions we can see from the regions we cannot is called the cosmic horizon. It is not a physical barrier. It is simply the edge of the observable universe. Beyond it, there is almost certainly more universe, more galaxies, more stars, more planets. But we are cut off from it forever. This is one of the great frustrations and wonders of cosmology. We know there is more out there, but we cannot see it. We can only make educated guesses based on what we can observe, and what we can observe is enough to fill a lifetime of wonder. Let me give you some numbers to help picture the scale. The Earth is about 8,000 miles in diameter. If you drove around the equator at highway speed without stopping, it would take you about 2 weeks. The Sun is about 860,000 miles in diameter. More than 100 Earths could fit across it. The distance from the Earth to the Sun is about 93 million miles. Light covers that distance in a little over 8 minutes. The distance to the edge of our solar system, out where the comets drift in the cold darkness, is about 9 billion miles. Light takes about 13 hours to get there. The nearest star, Proxima Centauri, is about 25 trillion miles away. That is more than 4 light years. The Milky Way galaxy is about 100,000 light years across. It contains somewhere between 100 billion and 400 billion stars. The nearest large galaxy, Andromeda, is about 2.5 million light years away. In about 4 billion years, the Milky Way and Andromeda will collide and merge into a single giant galaxy. The Virgo cluster, a nearby collection of galaxies, is about 54 million light years away. The most distant galaxies Webb has photographed are about 13 billion light years away, measured by how long the light has been traveling. But because of cosmic expansion, those galaxies are now about 30 to 40 billion light years away. The observable universe as a whole is about 93 billion light years in diameter, and beyond that, there is more. How much more, we do not know. These numbers are so large that they lose meaning. Our brains evolved to understand distances we could walk or throw a spear. We have no intuition for trillions of miles or billions of years. The best we can do is use analogies and comparisons to get a rough sense of the immensity. Here is one that might help. If you shrank the sun down to the size of a grain of sand, then on that scale, the nearest star would be about 4 miles away. The Milky Way would be about the size of the continental United States, and the observable universe would be about the size of Earth's orbit around the Sun. That is the scale we are dealing with, and Webb is helping us explore it. One of the ways Webb explores the universe is by creating what astronomers call deep fields. A deep field is an image made by pointing the telescope at a small patch of sky and collecting light for a very long time. Hours, days, even weeks. By stacking all those photons together, the telescope can see incredibly faint objects that would be invisible in a shorter exposure. The first famous deep field was the Hubble Deep Field, taken in 1995. Astronomers pointed Hubble at a seemingly empty patch of sky, about the size of a tennis ball seen from 100 feet away. They let the telescope stare at that spot for 10 days. When they processed the image, they found it was packed with galaxies, nearly 3,000 of them in that tiny sliver of sky. The image showed that what looked like emptiness was actually teeming with distant worlds. Hubble went on to take even deeper images. The Hubble Ultra Deep Field, taken in 2004, revealed about 10,000 galaxies in a slightly larger patch. Some of the light in that image had been traveling for over 13 billion years. Webb has now taken its own deep fields, and they are stunning. The first Webb Deep Field image was released in July 2022. It showed a galaxy cluster called SMACS 0723, about 4 billion light-years away. But the cluster was just the foreground. Behind it, distorted by gravitational lensing, were thousands of even more distant galaxies. Some of them were among the oldest ever seen at the time. Since then, Webb has taken even deeper images. The JADES program, short for the James Webb Space Telescope Advanced Deep Extragalactic Survey, has photographed some of the most distant galaxies ever detected. In one small patch of sky, the JADES team found more than 700 galaxies from the first billion years of the universe. 93% of them had never been seen before. Every deep field is a core sample of cosmic history. By counting the galaxies and measuring their properties, scientists can figure out how the universe changed over time, how many galaxies existed at different epochs, how fast they were forming stars, how they grew and evolved. And the story these deep fields tell is remarkable. Galaxies were forming earlier and faster than anyone expected. The universe was not a slow builder. It hit the ground running. This is the crisis Webb has created. Not a bad crisis, a scientific crisis, the kind that forces us to rethink what we know and come up with better ideas. For decades, astronomers have relied on a model of the universe called Lambda CDM, often pronounced lambda cold dark matter. This model describes a universe dominated by dark energy, symbolized by lambda, and cold dark matter, which is dark matter made of slow-moving particles. Lambda CDM has been incredibly successful. It explains the cosmic microwave background with exquisite precision. It predicts how galaxies cluster on the larger scales. It matches observations of supernovae and cosmic expansion. For years, it has been the gold standard of cosmology. But Webb is finding cracks in the model. The early massive galaxies are one problem. Lambda CDM predicts that galaxies should have grown gradually, building up mass over billions of years. The universe breakers that Webb has found do not fit this picture. The Hubble tension is another problem. Lambda CDM predicts a certain expansion rate for the universe, and the observed rate does not match. The supermassive black holes are yet another problem. Lambda CDM does not easily explain how such massive objects could have formed so quickly. None of these problems are fatal to the model. Scientists are clever, and they may find ways to tweak Lambda CDM to accommodate the new observations. But the accumulating anomalies suggest that something deeper might be going on. There might be physics we do not yet understand, forces or particles we have not discovered, aspects of space, time or gravity that our equations do not capture. This is actually exciting. Science advances when observations do not match expectations. The gaps in our knowledge are where discoveries hide. Webb is shining a light into those gaps, revealing new puzzles for us to solve. One possibility that scientists are exploring is early dark energy. In the standard model, dark energy is constant. It has the same strength everywhere and at all times. But what if dark energy was stronger in the early universe and then faded away? This early burst of dark energy could have given the universe a kick, speeding up its expansion and potentially allowing galaxies and black holes to form faster. Early dark energy is just one idea. There are others. Maybe dark matter is not as cold as we thought. Maybe it interacts with itself in ways we have not considered. Maybe gravity works differently on very large scales or at very early times. Maybe there are extra dimensions of space that affected how the universe evolved. All of these ideas are speculative. None of them has strong evidence yet. But that is how science works. You make observations, you find anomalies, you propose explanations, you test them, and eventually you inch closer to the truth. Webb is giving us the observations, the anomalies, the raw material for new ideas. What happens next depends on the ingenuity of scientists around the world. Let us shift gears and talk about something a little more personal. What does all this mean for us, for life, for our place in the universe? One of the reasons we study the cosmos is to understand where we came from. The atoms in your body were forged in the hearts of stars. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was cooked up in stellar furnaces billions of years ago. When those stars exploded, they scattered their contents across space. That material gathered into new clouds, collapsed into new stars and planets, and eventually became you. You are literally made of star stuff. This is not poetry. It is chemistry. It is physics. It is the story of how complex matter emerged from a universe that started with only hydrogen and helium. Webb is helping us trace this story. By studying the first galaxies and the first stars, we learn about the origins of the heavy elements that make life possible. We see the cosmic forges where those elements were created. We watch the supernovae that spread them across the universe. But Webb is also looking for life directly, or at least for the conditions that might support life. The search for exoplanet atmospheres is part of this quest. If we find a rocky planet with an atmosphere rich in water vapor and oxygen, that would be a strong hint that something biological might be happening there. Oxygen is highly reactive. It does not stick around for long unless something is constantly producing it. On Earth, that something is photosynthesis. Plants and algae pump out oxygen as a byproduct of their metabolism. Finding oxygen on an exoplanet would not prove there is life. There could be other explanations, but it would be a tantalizing clue, enough to warrant much more study. Webb has not found such a signal yet. The exoplanets it has studied so far are mostly too hot or too harsh to host life as we know it. But the search continues. TRAPPIST-1e is a promising target. So are other rocky planets in habitable zones around nearby stars. In the coming years, as Webb continues to observe and as new telescopes come online, we may get closer to answering the biggest question of all. Are we alone? The sheer scale of the universe suggests we might not be. With trillions of galaxies and countless stars and planets, it seems almost impossible that Earth is the only place where life arose. The universe has had nearly 14 billion years to experiment. It would be strange if we were the only result. But we have no evidence yet. No confirmed signals from alien civilizations. No definitive biosignatures in exoplanet atmospheres. The universe is vast and old, but it is also silent. Or at least, we have not learned to hear its whispers. This is sometimes called the Fermi paradox, named after physicist Enrico Fermi. If the universe is so big and so old, and if life arises naturally under the right conditions, then where is everybody? Why have we not detected any signs of other intelligent beings? There are many possible answers. Maybe intelligent life is rare. Maybe it tends to destroy itself. Maybe civilizations are spread so far apart that they never make contact. Maybe they are there, but we do not recognize the signals. Maybe we have simply not looked hard enough. Webb will not solve the Fermi paradox, but it will give us more data to work with, more planets to study, more atmospheres to probe, more pieces of the puzzle. And even if we never find aliens, the universe Webb is revealing is breathtaking. The colors of distant nebulae, the swirling arms of ancient galaxies, the birth cries of infant stars, the ghostly glow of cosmic dust. Every image is a work of art, painted by nature over billions of years. We live in a universe of staggering beauty and complexity. We are small, yes, brief flickers in the cosmic night, but we are also the part of the universe that has learned to look at itself and wonder. That is not nothing. That is everything. Now let us talk about the architecture of the universe, because the cosmos is not just a random scattering of galaxies floating in empty space. It has structure, pattern, organization on scales so vast that it defies imagination. If you could zoom out far enough, you would see that galaxies are not evenly distributed. They cluster together in groups and larger collections. Our Milky Way is part of a small gathering called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and about 80 smaller galaxies. The Local Group spans about 10 million light-years. But the Local Group is just a tiny part of a much larger structure called the Virgo supercluster. This collection of galaxy clusters and groups stretches across more than 100 million light-years. At its center is the Virgo cluster, a massive concentration of over 1,000 galaxies held together by gravity. And the Virgo supercluster is itself part of something even bigger. In 2014, astronomers mapped out a structure they called Laniakea, which means immense heaven in Hawaiian. Laniakea is a supercluster of superclusters, containing more than 100,000 galaxies spread across 500 million light-years. Every galaxy within Laniakea, including our own, is being pulled toward a mysterious region called the Great Attractor. We cannot see the Great Attractor directly because it lies behind the dense star fields of the Milky Way's central bulge. Dust and gas block our view, but we can see its gravitational influence. Galaxies across a huge swath of the universe are being tugged in its direction. What is the Great Attractor? It is probably a concentration of mass, a knot of galaxies and dark matter that warps the fabric of space and pulls everything nearby toward it. But the details remain mysterious. It is one of many cosmic puzzles that Webb may help solve. Beyond Laniakea, the universe continues to reveal structure. There are other superclusters, each containing their own thousands of galaxies. And between these superclusters are voids, immense bubbles of nearly empty space, hundreds of millions of light-years across, where galaxies are rare. The pattern of superclusters and voids forms what scientists call the cosmic web. If you could see the entire observable universe at once, it would look like a vast, three-dimensional network of glowing threads and dark gaps. The threads are the filaments of galaxies and dark matter. The gaps are the voids. This web was not designed. It emerged naturally from the physics of the early universe. Right after the Big Bang, matter was spread almost perfectly evenly. But there were tiny fluctuations, slight differences in density from place to place. These fluctuations were imprinted by quantum physics during the period of cosmic inflation. Over billions of years, gravity amplified these tiny differences. Regions with slightly more matter pulled in even more matter. Regions with slightly less matter lost what little they had. The rich got richer and the poor got poorer. The result was the web of filaments and voids we see today. Webb is helping us understand how this web formed and evolved. By observing the most distant galaxies, scientists can see the web as it was in its youth. They can trace how filaments grew, how voids expanded, how clusters assembled from smaller pieces. One remarkable finding is that the early universe already had structure. Even in the first billion years, galaxies were not randomly scattered. They were beginning to cluster. They were starting to organize along filaments. The cosmic web was already taking shape. This is important because it tells us something about the nature of dark matter. If dark matter were made of fast-moving particles, it would smooth out the early structure and prevent filaments from forming quickly. But the fact that we see structure so early suggests that dark matter really is cold, made of slow particles that clump easily. Webb is also finding evidence that galaxies grow by merging with each other. In the early universe, galaxies collided frequently. They smashed together, their stars and gas mixing and triggering bursts of new star formation. Over time, these collisions built up the massive galaxies we see today. This process continues even now. The Milky Way is currently digesting several smaller galaxies that have fallen into it. In a few billion years, it will merge with Andromeda in a spectacular cosmic collision. The two spiral galaxies will swirl around each other, distorting into strange shapes, eventually settling into a single giant elliptical galaxy. Collisions between galaxies are not as violent as they might sound. Galaxies are mostly empty space. The stars within them are so far apart that when two galaxies collide, their stars almost never actually hit each other. It is like two swarms of bees passing through each other. But the gravitational forces involved are tremendous. They reshape the galaxies, compress clouds of gas, and trigger the birth of millions of new stars. Webb has photographed many examples of colliding and interacting galaxies. One famous image shows a pair of galaxies known as ARP 107. Their interaction has stretched and distorted them, giving them the appearance of a ghostly face with two glowing eyes and a faint smile. It is a beautiful reminder that the universe is dynamic, constantly changing on timescales that dwarf human history. Let us go deeper into the physics of light and how Webb uses it to unravel cosmic mysteries. Light is made of particles called photons. Each photon carries a specific amount of energy, which determines its wavelength. High-energy photons have short wavelengths and appear blue or violet to our eyes. Low-energy photons have long wavelengths and appear red. Even lower-energy photons have wavelengths so long that we cannot see them at all. They are infrared. When a photon travels through expanding space, something interesting happens. The expansion stretches the space the photon is traveling through. This stretches the photon itself, increasing its wavelength. A photon that started out as blue visible light can be stretched into green, then yellow, then orange, then red, and eventually into infrared. This is why distant galaxies look red. Their light has been redshifted by the expansion of the universe. The farther away the galaxy, the longer the light has been traveling, and the more it has been stretched. By measuring how much a galaxy's light has been redshifted, astronomers can figure out how far away it is and how long ago the light was emitted. Webb's ability to see infrared light is what makes it so powerful for studying the early universe. The most distant galaxies have light that has been redshifted completely out of the visible spectrum. Hubble, which mostly sees visible light, could not detect them. But Webb can. Webb also uses infrared light to see through dust. Cosmic dust is made of tiny grains of carbon, silicon, and other materials. It is everywhere in the universe, filling the spaces between stars and blocking visible light like fog blocking a flashlight. But infrared light can pass through dust much more easily. It has longer wavelengths that can slip between the dust grains. This is why Webb can peer into star-forming regions that are hidden from other telescopes. Newborn stars are surrounded by thick cocoons of dust and gas. In the visible light, they are invisible. But in infrared, they glow like embers, revealing their presence. Webb has captured stunning images of stellar nurseries, regions where new stars are being born. The Carina Nebula, the Eagle Nebula, the Orion Nebula, all of these famous sites of star formation have been revealed in new detail by Webb's infrared eyes. Pillars of gas and dust, sculpted by the radiation from nearby hot stars, tower like mountains in space. Within them, hidden from view until now, are baby stars just beginning to shine. These images are not just beautiful. They are scientific data. By studying the structure of these nebulae, the temperature and density of the gas, the types of molecules present, scientists learn how stars form. They trace the process from cold, collapsing cloud to hot, shining star. Webb has also made surprising discoveries about the composition of interstellar dust. The dust contains complex organic molecules, including some that are building blocks of life. Carbon-based rings and chains, the kinds of structures found in amino acids and other biological molecules, are scattered throughout the cosmos. This does not mean there is life floating between the stars. These molecules are not alive, but they do show that the universe is primed for life. The ingredients are everywhere. Given the right conditions, a planet, liquid, water, energy sources, these molecules could be assembled into something that lives and reproduces and evolves. We are made of this stuff. The carbon in our bodies was forged in stars and scattered into space as dust. It drifted through nebulae, got swept up into a collapsing cloud, and eventually became part of the Earth and everything on it. Webb is showing us the cosmic factory that produced the atoms we are made of. Let us return to the question of scale, because I want to make sure you truly feel how immense the universe is. The fastest spacecraft humans have ever built is the Parker Solar Probe. At its closest approach to the Sun, it travels at about 430,000 miles per hour. That is faster than any other human-made object in history. At that speed, how long would it take to reach the nearest star, Proxima Centauri? About 6,000 years, just to reach our nearest neighbor. How long would it take to cross the Milky Way? At 430,000 miles per hour, it would take about 170 million years. How long would it take to reach the Andromeda Galaxy? About 4 billion years. By the time you got there, the Sun would have already swelled into a red giant and swallowed the Earth. How long would it take to cross the observable universe? At the speed of the Parker Solar Probe, it would take about 140 trillion years. That is more than 10,000 times the current age of the universe. These numbers are so large they become absurd. No spacecraft we can imagine would ever cross such distances. Even light, the fastest thing in the universe, takes billions of years. This is why telescopes are so important. We cannot travel to distant galaxies. We cannot visit the early universe, but we can see them. We can collect their light and learn their secrets. Webb is our window into the cosmos. Through it, we witness events that happened billions of years ago in places we will never reach. It is the closest thing we have to time travel. And here is something profound to consider. The light Webb collects has been traveling for billions of years. It left its source long before Earth existed, long before the Sun ignited, long before the atoms in your body had even formed. That light is ancient, and yet it is only now reaching us, only now becoming part of our experience. When you look at a Webb image of a distant galaxy, you are not seeing a photograph of something that exists right now. You are seeing a ghost, an echo, a message from the past that has finally arrived. The galaxy you are looking at may have changed beyond recognition since that light left. It may have merged with other galaxies. It may have been torn apart by tidal forces. It may no longer exist as a separate object at all. This is the strange reality of observational astronomy. We only ever see the past. The present state of distant objects is hidden from us by the speed of light itself. But there is a flip side to this. Because light takes time to travel, we can see the universe at different ages, just by looking at different distances. Close objects show us the recent universe. Distant objects show us the ancient universe. The sky is a time machine, displaying cosmic history at every depth. Webb is reading that history like a book. Each galaxy is a sentence. Each cluster is a paragraph. Each deep field is a chapter. Together, they tell the story of how the universe evolved from a hot, featureless plasma to the intricate web of galaxies and stars we see today. Let me describe some of what Webb has found in more detail. One of the telescope's most celebrated images is the Carina Nebula's cosmic cliffs. This image shows a boundary between a dense cloud of gas and the empty space beyond. The cloud is being eaten away by intense radiation from young, hot stars just outside the frame. The edge of the cloud looks like the coastline of a continent seen from space, with peaks and valleys and intricate texture. But look closer, and you see something amazing. Scattered along the edge of the cloud are tiny jets and knots. These are newborn stars, still embedded in the dust from which they formed. Some of them are shooting out beams of material at incredible speeds, clearing paths through the surrounding gas. These jets are the birth cries of stars, announcing their arrival to the universe. Before Webb, many of these young stars were invisible. They were hidden behind curtains of dust. Webb's infrared vision pierced the veil and revealed them for the first time. Another spectacular image shows the Southern Ring Nebula, a shell of gas blown off by a dying star. The star at the center was once similar to our Sun. As it aged, it puffed up into a red giant and shed its outer layers into space. What remains is a tiny, hot core called a white dwarf, slowly cooling in the center of the expanding shell. Webb's image of the Southern Ring Nebula revealed something surprising. There is not one star at the center, there are two. The second star had been hidden in previous images. It is a companion, locked in orbit with the dying star. The interaction between the two stars shaped the nebula, creating the complex patterns of rings and arcs that we see. This is a good example of how Webb's clarity is revealing hidden details that change our understanding of objects we thought we knew well. The Southern Ring Nebula has been studied for decades, but only Webb showed us its true structure. Webb has also made groundbreaking observations of planets in our own solar system. Jupiter, Saturn, Neptune, Mars, each has been photographed in infrared light, revealing features invisible to ordinary cameras. The image of Jupiter is particularly stunning. The giant planet glows with bands of infrared light, revealing the heat rising from deep within its atmosphere. The Great Red Spot, a storm larger than Earth that has been raging for centuries, appears as a dark silhouette against the bright background. Around Jupiter, the faint rings that were only discovered in the 1970s are visible in exquisite detail. Saturn's rings are even more impressive. Webb photographed them in infrared, revealing the differences in composition between different ring bands. Some regions are icy and reflective. Others are darker, possibly contaminated with dust or organic material. The image also shows Saturn's atmosphere, with subtle bands and storms that rival Jupiter's. Neptune, the most distant planet in our solar system, was revealed in unprecedented detail. Its faint rings, which had only been photographed by the Voyager 2 spacecraft during its brief flyby in 1989, are clearly visible in Webb's image. The planet's atmosphere shows cloud patterns and a dark spot similar to the ones seen on Jupiter and Saturn. Even Mars, our close neighbor, looks different in Webb's infrared gaze. The telescope detected carbon dioxide and other molecules in the Martian atmosphere, demonstrating its ability to study planetary compositions from nearly 100 million miles away. These observations of our own planets are practice runs for studying planets around other stars. The techniques Webb uses to analyze Jupiter's atmosphere can be applied to hot Jupiters orbiting distant suns. The methods used to detect gases on Mars can be scaled up to search for biosignatures on potentially habitable worlds. Webb is versatile. It can zoom in on nearby planets and zoom out to the edge of the observable universe. It can study individual stars and survey vast cosmic structures. It is the Swiss Army knife of astronomy, capable of tackling almost any question we can think to ask. And we are asking a lot of questions. How did the first stars form? What triggered reionization? Why are early galaxies so bright? What are little red dots? How do supermassive black holes grow so fast? Is the Hubble tension real, and what does it mean? Do rocky planets around red dwarfs have atmospheres? What is dark matter? What is dark energy? Are we alone? Webb will not answer all of these questions. Some will take decades more. Research. Some might require telescopes that have not been built yet. But Webb is making progress on all of them. It is advancing our knowledge on every front, filling in details that were blank just a few years ago. The universe is slowly coming into focus. Where there was mystery, there is now data. Where there was darkness, there is now light. That is what makes this moment in history so exciting. We are living through a revolution in our understanding of the cosmos. Future generations will look back at this era, at the years when Webb first opened its eyes, and see it as a turning point. The moment when we truly began to grasp the scale and complexity of existence. And we are only getting started. Let us dive even deeper into some of the specific things Webb has discovered, because the details are where the wonder lives. Consider the process of star formation. We know the basic outline. A cloud of gas collapses under its own gravity. The center gets hot and dense. Eventually, nuclear fusion ignites, and a star is born. But the details are incredibly complex, and Webb is revealing them in ways we never expected. Stars do not form in isolation. They form in groups, in clusters, in sprawling complexes that can span hundreds of light years. Within these star-forming regions, the interplay of gravity, radiation, magnetic fields, and turbulent gas creates intricate structures. Pillars of dense gas tower like mountains, sculpted by the radiation from nearby hot stars. Cavities and bubbles mark the sites where previous generations of stars exploded. Filaments of dust snake through the clouds, channeling material toward collapsing cores. Webb has photographed all of this in exquisite detail. In the Carina Nebula, it revealed hundreds of previously hidden young stars, many of them still surrounded by the disks of gas and dust from which planets might form. In the Tarantula Nebula, a giant star-forming region in a nearby galaxy, Webb showed the intricate nests where massive stars are being born. In the Eagle Nebula, home of the famous pillars of creation, Webb's infrared vision penetrated the dusty columns to reveal the embryonic stars within. One surprising finding is that star formation seems to be more efficient in the early universe than in the universe today. Galaxies from the cosmic dawn were converting gas into stars at a remarkable rate. Some of them were forming stars 10 or even 100 times faster than the Milky Way does now. Why would early star formation be so efficient? One possibility is that the gas in early galaxies was different. It contained less heavy elements, fewer metals and dust particles. This might have changed how the gas cooled and collapsed. Cold gas can fall together more quickly, potentially forming stars faster. Another possibility is that star formation in the early universe happened in bursts. A galaxy might be quiet for millions of years, then suddenly explode with activity as a wave of star formation swept through it. These bursts would make early galaxies appear much brighter than they actually are on average. Webb is helping us distinguish between these possibilities by studying the populations of stars in early galaxies. Are they young and newly formed, or is there a mix of ages? Are they all similar, or is there variety? The answers will tell us how star formation worked in the universe's youth. Let me tell you about one particularly remarkable star that Webb has studied. It is called Earendel, and it is the most distant individual star ever detected. Most of the light we see from distant galaxies is the combined glow of billions of stars. We cannot pick out individual points of light because they are too far away and too faint. But Earendel is different. It is located in a galaxy about 12.9 billion light-years away, and by a cosmic coincidence, it lies almost exactly on a gravitational lens. A gravitational lens is created when a massive object, like a galaxy cluster, bends the light from more distant objects behind it. This bending can magnify and brighten the background objects, like a cosmic magnifying glass. Earendel happens to sit on what is called the critical curve of such a lens. This is the sweet spot where magnification is strongest. The galaxy cluster in front of it has amplified its light by thousands of times, making it visible to Webb even though it is so far away. When Earendel's light left on its journey to us, the universe was only about 900 million years old. This star is from the cosmic dawn, one of the earliest generations of stars ever seen. Webb's observations of Earendel revealed something intriguing. The star appears to be a blue supergiant, one of the hottest and brightest types of stars. It might be 50 to 100 times the mass of our Sun, and millions of times more luminous. But there might actually be two stars there, a binary system that happens to be aligned just right for maximum magnification. Earendel will not live long by stellar standards. Stars this massive burn through their fuel in just a few million years before exploding as supernovae. Earendel has almost certainly been dead for billions of years by now. The light we see is a final message from a star that died when the universe was young. There are likely many other individual stars in the early universe that gravitational lensing could reveal. Webb and future telescopes will hunt for them, giving us glimpses of the first generation of suns. Speaking of the first generation, let us talk about what scientists call population 3 stars. This is a technical term for a very poetic idea, the first stars that ever existed. When the universe was young, it contained only hydrogen, helium, and tiny traces of lithium. These are the elements forged in the Big Bang itself. There were no heavier elements, no carbon, no oxygen, no iron. The gas that would form the first stars was pristine, untouched by the nuclear furnaces that create heavy elements. Stars that form from this pure metal-free gas would have been very different from stars today. Without heavy elements to help the gas cool efficiently, the collapsing clouds would have been hotter and more turbulent. The result, according to computer simulations, would have been enormous stars, possibly hundreds of times the mass of our Sun. These population 3 stars would have burned hot and bright, shining with mostly ultraviolet light. They would have lived fast, just a few million years, before exploding in massive supernovae, or collapsing directly into black holes. Their deaths would have seeded the universe with the first heavy elements, the metals that would become part of the next generation of stars and eventually part of planets and people. We have never directly observed a population 3 star. They are too distant and too rare. By the time the universe is old enough for us to see clearly, the first stars are already gone, replaced by later generations that contain traces of metals. But Webb might find evidence of population 3 stars indirectly. When these massive stars exploded, they would have produced distinctive signatures in the gas around them, unusual ratios of certain elements, patterns that do not match normal supernovae. By studying the most ancient galaxies and looking for these chemical fingerprints, scientists hope to confirm that population 3 stars really existed. In late 2024, astronomers announced they may have found the first observational evidence of population 3 stars. A galaxy called GS 3073, seen as it was about 1.1 billion years after the Big Bang, shows an unusual abundance of nitrogen relative to oxygen. This ratio is hard to explain with normal stars but fits well with models of massive population 3 stars. If confirmed, this would be a major discovery. It would validate decades of theoretical predictions and give us a direct window into the very first stars that ever shone. Let us talk more about black holes, because they are among the most mysterious and fascinating objects in the universe. A black hole is a region of space where gravity is so strong that nothing can escape. Not matter, not light, not information. If you fell into a black hole, you would be stretched and crushed in ways that physics can barely describe. To an outside observer, you would appear to freeze at the boundary, the event horizon, and slowly fade to red as your light gets stretched into longer and longer wavelengths. Black holes come in different sizes. Stellar mass black holes, formed when massive stars collapse at the end of their lives, contain a few times the mass of our Sun. Supermassive black holes, found at the centers of galaxies, contain millions or billions of solar masses. There may also be intermediate mass black holes, containing thousands of solar masses, though these are harder to find. Webb is particularly interested in supermassive black holes because they seem to play a crucial role in how galaxies form and evolve. At the center of almost every large galaxy, including our own, Milky Way, sits a supermassive black hole. These behemoths do not just passively lurk in the galactic core. They interact with the galaxy around them. When gas falls toward a supermassive black hole, it spirals inward, heating up and glowing brightly. This creates what is called an active galactic nucleus, or AGN. The brightest AGN are called quasars, and they can outshine entire galaxies. The radiation from an AGN can push gas out of a galaxy, shutting down star formation, or it can compress nearby clouds, triggering new star formation. The balance between these effects determines how a galaxy grows and changes over time. Webb has found supermassive black holes that seem impossibly large for their age. In galaxies from the first billion years of the universe, it has detected black holes containing hundreds of millions of solar masses. These black holes are so massive that they challenge our understanding of how such objects form and grow. There are a few possibilities. Maybe supermassive black holes started from massive seeds, not ordinary stellar black holes, but something much heavier. Direct collapse black holes, formed when giant clouds of gas collapsed without forming stars first, could have started out with masses of 100,000 suns or more. Another possibility is that black holes grew extremely fast in the early universe. If enough gas was available, and if conditions were just right, black holes might have gobbled up material faster than the usual limits would suggest. This is called super-Eddington accretion, and it remains controversial. A third possibility is that we are misinterpreting the data. Maybe some of the objects Webb sees are not supermassive black holes at all, but something else that mimics their signatures. Scientists are being careful to check their work before drawing firm conclusions. Whatever the explanation, the presence of these massive black holes so early in cosmic history is reshaping our understanding of how galaxies and their central engines co-evolved. One class of objects that has particularly intrigued astronomers is the little red dots we mentioned earlier. These are compact, very red sources that show up in Webb's deepest images. At first, their nature was unclear. Were they distant galaxies? Were they quasars? Were they something new? After careful study, it appears that little red dots are a diverse class. Some are indeed distant galaxies, whose light has been reddened by dust. Others are active galactic nuclei, quasars shrouded in veils of dust that block their blue light and let only red light through. And some might be something more exotic, objects that do not fit neatly into existing categories. One little red dot, nicknamed the cliff because of a distinctive feature in its spectrum, turned out to be particularly strange. Its light shows what is called a Balmer break, a sudden drop in brightness at a specific wavelength. Balmer breaks usually come from stars, so astronomers expected the cliff to be a galaxy full of old stars. But when they looked more closely, the data did not fit that story. The Balmer break was too extreme, too sudden. It looked less like a galaxy of stars and more like a single, very hot, very massive object. A team of astronomers proposed a radical explanation. Maybe the cliff is what they called a black hole star, a supermassive black hole surrounded by a thick envelope of hot hydrogen gas. This gas would absorb and re-emit light in a way that mimics the signature of an entire galaxy. If black hole stars are real, they might represent a phase in the early evolution of supermassive black holes, a period when the black hole was still growing, still surrounded by its birth material, before it cleared away the gas and became a naked AGN. This is speculative. The idea needs more testing, more observations, more theoretical work. But it shows how Webb is forcing astronomers to think creatively, to consider possibilities they might have dismissed before. Let us change scales again and think about the most fundamental question Webb can help answer. What is the universe made of? We have already talked about dark matter and dark energy. Together, they make up about 96% of the universe's total content. But what about the remaining 4%, the stuff we can actually see and touch? This ordinary matter is called baryonic matter because it is made of protons and neutrons, which are types of particles called baryons. Baryonic matter includes stars, planets, gas clouds, dust, people, everything you have ever seen or touched. But here is a strange fact. Even the baryonic matter in the universe is mostly invisible. We can see stars and gas when they emit light, but much of the ordinary matter is in forms that do not glow. It lurks in the spaces between galaxies, in thin halos around galaxies, in cold clouds that never formed stars. This hidden baryonic matter is called the missing baryons, and finding it has been a challenge for astronomy. Computer simulations predict that about half of the ordinary matter in the universe should be in these diffuse, hard-to-detect forms. Observational evidence has been slowly catching up. Webb is contributing to this search by studying the gas around and between galaxies. When light from a distant quasar passes through a cloud of gas, the gas absorbs certain wavelengths of light. By analyzing these absorption features, astronomers can figure out what the gas is made of, how dense it is, and how it is moving. Webb's infrared spectrograph is particularly good at detecting certain molecules and ions in intergalactic gas. It can measure the temperature and composition of gas that other telescopes miss. This is helping to build a more complete picture of where all the ordinary matter in the universe is hiding. Understanding the distribution of matter, both dark and baryonic, is crucial for understanding how the universe evolved. Matter is the raw material from which everything is built. Galaxies, stars, planets, life, all of it, comes from matter that was spread through space after the Big Bang. The cosmic web we discussed earlier is the map of how that matter is distributed today. Webb is helping us trace that map back in time, to see how it formed and changed over billions of years. Every observation Webb makes adds another piece to the puzzle. A piece of the scale, the structure, the history, the composition of the cosmos. Each piece on its own might seem small, but together they form a picture of reality that is breathtaking in its scope. We are learning the shape of the universe, its past, its present, and hints of its future. We are discovering that it is bigger, older, stranger, and more beautiful than we ever imagined, and we are learning our place within it. Now let us confront the crisis head-on, because what Webb is showing us is not just surprising, it is potentially revolutionary. For decades, cosmologists have built a model of the universe that works remarkably well. This model, Lambda CDM, explains the cosmic microwave background with precision down to parts per million. It predicts the large-scale structure of the universe, the distribution of galaxies and clusters with impressive accuracy. It accounts for the accelerating expansion, the abundances of light elements, and countless other observations. Lambda CDM is one of the great achievements of modern science. It distills the entire history of the universe into a few numbers: the density of matter, the density of dark energy, the rate of expansion, the age of the cosmos. These numbers have been measured and refined over decades of careful observation. But now, that model is under strain. The problems are piling up. The early massive galaxies that should not exist, the supermassive black holes that grew too fast, the Hubble tension that refuses to go away, the hints that reionization happened differently than expected. Each of these issues, by itself, might be dismissed as a statistical fluke or an observational error, but together they form a pattern that suggests something is missing from our picture. Let me be clear about what this means. It does not mean that the Big Bang did not happen. The evidence for the Big Bang is overwhelming and comes from many independent sources. The cosmic microwave background, the abundance of hydrogen and helium, the expansion of the universe, all of these point to a hot, dense beginning about 13.8 billion years ago. It does not mean that dark matter and dark energy do not exist. The evidence for these is also strong, even if we do not know exactly what they are. What it means is that the details of how the universe evolved, from that hot beginning to the cosmos we see today, may be more complicated than we thought. There may be physical processes we have not accounted for. There may be components of the universe we have not yet discovered. There may be aspects of gravity or space-time that our equations do not capture. This is not a failure of science. This is science working as it should. We make models. We test them against observations. When the observations do not match, we revise the models. The process is slow and messy, but it is how we approach the truth. Webb is providing the observations that are forcing the revision, and that is incredibly valuable. One area where revision might be needed is our understanding of the very early universe. The period right after the Big Bang, before the first stars formed, is still poorly understood. We have a general picture: inflation followed by cooling, followed by structure formation, but the details are fuzzy. What if there was a brief period of extra dark energy right after the Big Bang? This early dark energy could have given the universe a boost, accelerating the expansion and creating conditions that allowed galaxies to form faster. It could explain why we see so many bright galaxies so early. It could also explain the Hubble tension, because it would change the relationship between the early and late universe expansion rates. Early dark energy is just one idea. There are others. What if dark matter is not quite as cold as we assumed? Cold dark matter moves slowly and clumps efficiently. But what if some of the dark matter is warm, made of particles that move a bit faster? This would suppress the formation of small-scale structure, but might allow large structures to form in unexpected ways. What if gravity itself works differently on cosmological scales? General relativity has been tested extensively in the solar system and in binary pulsar systems, and it passes every test. But those tests are on relatively small scales compared to the size of the universe. Maybe gravity has subtle corrections that only become important over billions of light years. What if there are additional particles or forces we have not discovered? The standard model of particle physics describes the known particles with great precision, but it doesn't include dark matter or dark energy. There might be a whole sector of physics, a hidden universe of particles and interactions that we have not yet detected. All of these ideas are speculative. None of them has been confirmed, but they show the range of possibilities that scientists are exploring as they try to make sense of Webb's discoveries. The next few years will be crucial. Webb will continue to observe, gathering more data on early galaxies, distant black holes, and cosmic structure. Other telescopes, on the ground and in space, will contribute their own observations. Theorists will develop new models and make predictions that can be tested. Eventually, a cheery new picture will emerge. It might be a modified version of Lambda CDM, with extra ingredients added to account for the anomalies. Or it might be something more radical, a fundamentally new understanding of the cosmos. Whatever it is, it will be closer to the truth than what we have now. And that is what matters. Let us step back and appreciate the magnitude of what we are witnessing. 100 years ago, we did not know there were other galaxies. We thought the Milky Way was the entire universe. Then Edwin Hubble showed us that the fuzzy nebulae we saw through telescopes were actually island universes, each containing billions of stars. The universe suddenly got much, much bigger. 50 years ago, we discovered the cosmic microwave background and confirmed the Big Bang theory. We learned that the universe had a beginning, that it was once infinitely hot and dense, that it has been expanding and cooling ever since. 30 years ago, we discovered that the expansion of the universe is accelerating, driven by some mysterious dark energy that fills all of space. We learned that most of the matter in the universe is invisible dark matter, guiding the formation of galaxies through its gravitational pull. Now, with Webb, we are witnessing another leap. We are seeing the early universe directly, watching galaxies and black holes form in real time. We are finding that the cosmos is even more complex and surprising than we imagined. Each generation of astronomers has expanded our understanding of the universe. Each generation has discovered that reality is larger, stranger, and more wonderful than the generation before. We are the latest in that long line, standing on the shoulders of everyone who came before. And Webb is our tool, our eye, our window into the infinite. The telescope itself is a marvel of engineering. It took 25 years and $10 billion to build. It had to be designed to unfold in space, like an origami flower blooming in the cold darkness. Its sunshield, the size of a tennis court, protects the instruments from the heat of the sun. Its mirrors, coated in a layer of gold, just a few atoms thick, focus infrared light from the farthest reaches of the cosmos. Getting Webb to work was one of humanity's greatest technical achievements. The launch had to be perfect. The deployment had to be perfect. The calibration had to be perfect. Any major failure would have ended the mission. But everything worked. The telescope exceeded its specifications. It is performing even better than designed. Webb orbits the Sun at a special point called Lagrange 2, about 1 million miles from Earth. This point is balanced between the gravity of the Earth and the Sun, allowing the telescope to orbit with minimal fuel. It is always on the opposite side of the Earth from the Sun, keeping its instruments cold and dark. From this vantage point, Webb watches the universe. Day and night, it collects photons that have traveled billions of years to reach its mirrors. It sorts those photons by wavelength, measuring their energy and direction. It builds images and spectra, data that scientists download and analyze. The amount of data Webb produces is staggering. Each observation generates gigabytes of information. Teams of astronomers around the world compete for time on the telescope, proposing observations that might answer their most pressing questions. Only a fraction of proposals are accepted. Time on Webb is the most valuable resource in astronomy. And yet, Webb is generous. It shares its data with the public. Many of its images are released for everyone to see. You can download raw data from Webb and analyze it yourself if you have the skills. Science is happening in real time, visible to anyone who wants to follow along. This is a golden age for astronomy. Never before have we had such powerful tools. Never before have we learned so much so fast. The discoveries are coming in waves, each one revealing something new about the cosmos. Some of those discoveries are expected. Webb is filling in gaps that we knew existed, measuring things we knew needed measuring. But some discoveries are surprises, things we did not predict, things that challenge our assumptions and force us to think harder. The best telescopes are the ones that surprise us. They show us things we did not know we did not know. They expand not just our knowledge, but our imagination. Webb is one of those telescopes. Let me share a few more examples of what Webb has found. In the Orion Nebula, one of the closest star-forming regions to Earth, Webb discovered free-floating planets. These are planets that do not orbit any star. They drift through space alone, unattached, wandering through the nebula like cosmic orphans. Some of these free-floating planets come in pairs, orbiting each other. Astronomers are calling them Jupiter mass binary objects, or jumbos. They are puzzling because we do not know how they formed. Did they form like stars, collapsing directly from gas? Or did they form in planetary systems and later get ejected? The answer might tell us something important about how planets form in general. In the Serpens Nebula, Webb captured jets from a young star that stretch across 8 light years. These jets are made of hot gas, shot out along the star's rotational axis at incredible speeds. They plow into the surrounding material, creating shock waves and glowing knots of emission. The Serpens jets are among the most spectacular examples of stellar birth throes ever photographed. They show the violence of star formation, the way newborn stars announce themselves to the universe with screams of matter and light. Webb has also observed dying stars in unprecedented detail. The Butterfly Nebula, also known as NGC 6302, is a planetary nebula, the expanding remains of a star that shed its outer layers at the end of its life. Webb's images revealed a complex structure at the nebula's core, with jets and knots and a thick disk of dust surrounding the central white dwarf. Planetary nebulae were once thought to be relatively simple objects, spherical shells of gas expanding into space. But Webb is showing that they are far more intricate. They have jets, lobes, rings, and other structures shaped by the dying star's magnetic field, rotation, and companions. This complexity tells us that stellar death is not a quiet fade into darkness. It is an active, dynamic process, full of drama and beauty. Webb has even contributed to our understanding of objects within our own solar system. When the interstellar comet 3I Atlas passed through in 2025, Webb observed it to study its composition. Interstellar comets come from other star systems, carrying material that formed around alien suns. By studying them, we can learn about conditions in other planetary systems without traveling there. Closer to home, Webb has studied asteroids, Kuiper belt objects, and the moons of the outer planets. It has detected water ice on asteroids, measured the atmospheres of distant moons, and mapped the surfaces of worlds that spacecraft have never visited. The versatility of Webb is remarkable. It can study objects at any distance, from nearby moons to the edge of the observable universe. It can address questions in every branch of astronomy, from planetary science to cosmology. It is a true general-purpose observatory, limited only by the creativity of the scientists who use it. And those scientists are very creative. New proposals pour in constantly. Astronomers want to use Webb to study star formation in extreme environments, in the dense centers of galaxies and in the most metal-poor dwarf galaxies. They want to use it to map dark matter halos around distant galaxies. They want to use it to search for signs of life on exoplanets. They want to use it to push even deeper into the cosmic dawn, finding galaxies at redshifts of 15 or higher. Each observation builds on the ones before. Each discovery opens new questions. The pace of progress is exhilarating, and it shows no signs of slowing down. Webb was designed to last at least 5 years and possibly 10 or more. It carries fuel for station keeping and has redundant systems to survive component failures. If it performs as expected, it could be observing the universe well into the 2030s. That is a lot of time to explore, a lot of photons to collect, a lot of mysteries to solve. The universe is patient. It has been waiting for billions of years for someone to look at it and ask questions. Now finally, we are looking, we are asking, and the universe is answering. Not all at once, not completely, but bit by bit, the picture is becoming clearer. The scale is coming into focus. The story is being told. What will we find next? What surprise is waiting in the next deep field, the next spectrum, the next observation? Nobody knows. That is the thrill of discovery, the anticipation of the unknown. We are explorers, and the cosmos is our territory. Webb is our ship, carrying us across an ocean of darkness and light. And the voyage has only just begun. So what is the true scale of the universe, as revealed by Webb? Let me try to summarize what we have learned. The observable universe is about 93 billion light-years across. It contains at least 2 trillion galaxies, and possibly many times more. Each of those galaxies contains hundreds of billions of stars. The total number of stars in the observable universe is somewhere around a septillion, a 1 followed by 24 zeros. That is more stars than grains of sand on every beach on Earth. But the observable universe is probably just a tiny fraction of the whole. If cosmic inflation happened as theory predicts, the total universe could be vastly larger. It could be infinite. We might be specks in an ocean that has no shores. The universe is also old. 13.8 billion years have passed since the Big Bang. That is nearly 3 times the age of the Earth. It is long enough for generations of stars to live and die, for galaxies to form and merge, for the elements of life to be forged in stellar furnaces and scattered across space. And yet, the universe is also young in a sense. It has existed for only a tiny fraction of the time it will likely endure. If the universe keeps expanding, driven by dark energy, it will continue for trillions upon trillions of years. Stars will eventually burn out. Galaxies will drift apart. The cosmos will grow cold and dark. On that timescale, we are living in the bright morning of a very long day. The scale extends not just in space and time, but in complexity. The universe contains every kind of object imaginable. Planets of rock and ice and gas. Moons with volcanoes and oceans. Stars of every size and color. Neutron stars, spinning hundreds of times per second. black holes, warping space and time into knots, nebulae glowing with the light of newborn stars, galaxies, spiraling and elliptical and irregular, each one a universe of its own. And amid all this, there is us, creatures of carbon and water, living on a small rocky planet around an ordinary star in an unremarkable corner of an ordinary galaxy. We are made of the same atoms as the stars. We are part of the cosmic story, not separate from it. This is perhaps the most profound revelation of modern astronomy. We are not observers standing outside the universe, looking in. We are participants, embedded in the fabric of space and time, made of materials forged in cosmic fires. The iron in your blood was made in a supernova explosion. The oxygen you breathe was fused in the heart of a massive star. The calcium in your bones came from the death throes of suns that lived and died before our solar system was born. You are literally made of star stuff, recycled from ancient nuclear reactors scattered across the galaxy. This gives new meaning to the old question of our place in the universe. We are not strangers here. We are natives. We belong. The universe made us from its own materials, using its own processes. We are the universe looking at itself, wondering what it is. Webb is extending that gaze farther than ever before. Through its mirrors, we see the cosmos as it was billions of years ago, in places we will never visit. We witness the birth of galaxies, the death of stars, the formation of planets. We gather clues about how everything came to be, and we are learning that the universe is even more wonderful than we imagined. The early galaxies are bigger and brighter than expected. The first black holes are more massive. The cosmic web formed faster. Reionization happened earlier. The details of our models do not quite match the reality. This is not a failure. This is an invitation to learn more, to dig deeper, to understand better. The Hubble tension remains unresolved. The universe is expanding at a rate that does not make sense according to our best theories. Something is missing from the picture. What is it? We do not know yet, but Webb is helping us narrow down the possibilities. It is ruling out some explanations and pointing toward others. Eventually, the answer will emerge. Whatever that answer is, it will teach us something fundamental about the nature of reality. It might reveal new physics, new particles, new forces. It might change how we think about space, time, gravity, or energy. It might open doors to technologies and ideas we cannot yet imagine. This is the power of looking up, of asking questions, of building telescopes and pointing them at the darkness. The universe is not silent. It is speaking to us constantly, in the language of light. All we have to do is learn to read it. Let me leave you with some thoughts about what all this means. First, it means that curiosity is valuable. The urge to understand, to explore, to figure things out, is one of humanity's greatest traits. It drives us to ask questions that have no immediate practical application, but that expand our understanding of ourselves and our world. Webb exists because people wanted to know what was out there. That wanting, that pure curiosity, is worth celebrating and supporting. Second, it means that collaboration is possible. Webb was built by thousands of people from dozens of countries, working together over decades. Scientists, engineers, technicians, administrators, each contributed their piece to the whole. The telescope is a monument to what humans can achieve when they work toward a common goal. In a world often divided by conflict and competition, Webb is a reminder that cooperation is possible and powerful. Third, it means that the future is open. We do not know what we will discover next. We do not know what surprises are waiting in the data. The universe is vast and full of secrets. Some of those secrets might change everything we think we know. Others might confirm our theories and validate our methods. Either way, the journey of discovery continues. Fourth, it means that we are part of something larger than ourselves. The universe does not care about our petty concerns, our daily worries, our fleeting pleasures and pains. But it also does not diminish us. We are made of the same stuff as the stars. We are products of the same processes that built galaxies and shaped planets. Our brief lives are chapters in a story that has been unfolding for billions of years and will continue long after we are gone. There is a kind of comfort in that, and also a kind of responsibility. We are the part of the universe that has learned to ask questions. We are the part that builds telescopes and calculates orbits and names the constellations. If we do not do this, who will? The cosmos is indifferent but not hostile. It offers beauty to anyone who looks. It offers mystery to anyone who asks. It offers a sense of belonging to anyone who understands that they are part of it. Webb is our gift to the universe, our way of saying that we are here, we are paying attention, we want to know. And the universe is answering in the language of photons collected over billions of miles and billions of years. What will we find next? Nobody knows. That is the beauty of it. The next observation might reveal a galaxy older than any we have seen. It might find an exoplanet with an atmosphere rich in oxygen. It might detect a signal that does not fit any known source. It might uncover a clue that solves the Hubble tension or explains the origin of supermassive black holes. Or it might find something completely unexpected. Something that rewrites the textbooks. Something that makes us rethink everything. This is why we do science. Not just for the answers we find, but for the questions we discover. Each answer opens new questions. Each solved mystery reveals deeper mysteries. The more we learn, the more we realize how much there is to learn. The universe is not running out of secrets. It has plenty to share. So here is where we stand. The James Webb Space Telescope has revealed a universe that is bigger than we thought, older than we thought, more complex than we thought. It has found galaxies that challenge our models and black holes that defy our expectations. It has peered through dust and darkness to show us the birth of stars and the structure of distant worlds. It has confirmed some of our theories and cast doubt on others. Most importantly, it has reminded us why we look up, why we build these incredible machines and point them at the sky, why we spend billions of dollars and decades of effort to collect ancient photons from the edge of existence. We look up because we are curious, because we want to understand, because the universe is there and we are part of it, and we cannot help but wonder what it is and how it works and what our place might be within its vast expanse. That wonder is precious. It is the spark that drives discovery. It is the light that guides us through the darkness of ignorance. Webb is feeding that spark. Every image, every spectrum, every data point is fuel for the fire of curiosity. Scientists around the world are working through the data, making new discoveries, writing papers, sharing ideas. The conversation is global and ongoing, and you are part of it too. By watching this video, by learning about these discoveries, by wondering about the scale and nature of the universe, you are participating in one of humanity's greatest adventures. You are joining a tradition that stretches back to the first person who looked up at the night sky and wondered what the stars were. The universe is ours to explore. Not physically, perhaps. We may never travel to distant galaxies or walk on exoplanets. But mentally, intellectually, spiritually, the cosmos is open to us. We can learn its secrets. We can map its structures. We can trace its history and imagine its future. That is what Webb is helping us do. And it is only the beginning. The true scale of the universe is not just a number. It is not just 93 billion light years or 2 trillion galaxies or a septillion stars. The true scale is a feeling, a sense of awe, a recognition of how small we are and how vast everything else is, a humility mixed with pride, humility at our insignificance, pride at our ability to comprehend it. We are tiny, we are brief, we are fragile, but we are also curious, creative, and capable of wonder. We have built machines that can see the beginning of time. We have developed theories that explain the structure of reality. We have asked questions that no other species on Earth has ever asked. That is remarkable. That is worth celebrating. That is the true measure of humanity's place in the universe. Not our size, not our longevity, not our power, but our capacity to understand. Our desire to know. Webb is an expression of that desire, a $10 billion, million-mile-away expression of the human need to understand. And the universe is responding. It is showing us its face. Across billions of years and billions of light years, it is revealing its secrets, one photon at a time. So keep watching, keep wondering, keep asking questions. The universe is out there waiting to be understood, and we are just getting started. Thank you for joining me on this journey through the cosmos. If you enjoyed this exploration of the true scale of the universe, please like this video, subscribe to the channel, and share it with anyone who loves to wonder about the stars. Leave a comment below and tell me what you found most amazing. Until next time, keep looking up. Before we close, let me share a few more remarkable aspects of what Webb has discovered. Because the details matter, and every one of them adds to our appreciation of the cosmic tapestry. One thing Webb has shown us is that the universe was already diverse in its earliest days. We might have expected the first galaxies to all look similar, simple clumps of stars without much structure. But that is not what we find. Even in the first billion years, there were different types of galaxies. Some were compact and spherical. Others were already showing signs of spiral structure. Some were forming stars rapidly. Others were quieter, more settled. This diversity tells us that galaxy evolution is not a single path, but a branching tree. Different conditions lead to different outcomes. A galaxy that forms in a dense region of the cosmic web might evolve very differently from one that forms in a void. A galaxy that experiences an early merger might look nothing like one that grows in isolation. Webb is cataloging this diversity, building a census of early galaxies that will help us understand all the different ways a galaxy can form and grow. Every galaxy is a story, and Webb is collecting those stories from the most distant chapters of cosmic history. Another fascinating aspect is how quickly chemistry evolved in the early universe. When the first stars exploded, they released heavy elements into their surroundings. These elements mixed with the pristine gas and became part of the next generation of stars. Over time, the chemical composition of the universe changed. It became enriched with carbon, oxygen, iron, and all the other elements that would eventually become planets and people. Webb can measure the chemical composition of distant galaxies by analyzing the light they emit. Different elements produce distinctive patterns in the spectrum, like fingerprints. By reading these fingerprints, astronomers can tell what a galaxy is made of. The results have been surprising. Some early galaxies are more chemically enriched than expected. They contain more heavy elements than models predicted for such young objects. This suggests that star formation and stellar death happened even faster in the early universe than we thought. The first stars lived and died quickly, seeding their surroundings with the raw materials for the next generation. Webb has also found evidence of nitrogen in some early galaxies, which is particularly interesting. Nitrogen is made through specific nuclear processes that take time to develop. Finding lots of nitrogen in very early galaxies suggests that those processes were already at work, that the stellar populations in those galaxies were already mature enough to produce these elements. All of this chemistry matters because it sets the stage for life. Carbon is the backbone of organic molecules. Oxygen is essential for water. Nitrogen is a key component of DNA and proteins. The elements that make up your body were forged in stars and distributed across the cosmos. Webb is tracing that process back to its earliest stages. Let me also mention the importance of gravitational lensing in Webb's discoveries. Many of the most distant galaxies Webb has observed are magnified by the gravity of foreground galaxy clusters. These cosmic lenses bend and brighten the light from background objects, allowing us to see things that would otherwise be too faint to detect. Gravitational lensing is predicted by Einstein's general theory of relativity, and it has been observed many times. But Webb is using it more powerfully than ever before. By carefully choosing where to point the telescope, astronomers can exploit natural lenses in the sky to boost their reach. The downside of gravitational lensing is that it can distort images, stretching galaxies into arcs and rings. But these distortions also carry information. By modeling how a lens works, astronomers can figure out the mass distribution of the lensing cluster. This is one of the best ways to map dark matter, which is invisible but affects light through gravity. So gravitational lensing gives us a double benefit. It magnifies distant objects for study, and it reveals the invisible dark matter that does the magnifying. Webb is exploiting both of these benefits to learn about the universe on multiple scales. Another area where Webb is making progress is understanding how galaxies turn off their star formation. Some galaxies are actively forming new stars, burning bright with the light of young stellar populations. Others have stopped, their gas exhausted or expelled, their stellar nurseries quiet. This transition from star forming to quiescent is called galaxy quenching, and it is one of the big puzzles in astrophysics. What causes a galaxy to stop making stars? Is it something internal, like a supermassive black hole heating the gas, or something external, like interactions with other galaxies or the intergalactic medium? Webb is finding quenched galaxies surprisingly early in cosmic history. Some galaxies seem to have already stopped forming stars just 1 billion or 2 years after the Big Bang. This is faster than many models predicted. It suggests that whatever process quenches galaxies was already at work in the early universe. Understanding quenching is important because it affects the growth of galaxies over cosmic time. A galaxy that keeps forming stars will grow bigger and brighter. A galaxy that quenches early will stagnate, its stellar population aging without replacement. The balance between these fates determines the galaxy population we see today. Webb is also helping us understand the role of galaxy environments. Galaxies do not exist in isolation. They live in groups, clusters, and superclusters. They fall into dark matter halos and interact with their neighbors. These environmental effects shape how galaxies evolve. In dense environments like galaxy clusters, galaxies tend to be more quenched. They lose their gas through interactions with the hot intracluster medium. They get tidally stripped by the gravity of the cluster. They merge with other galaxies and change their structures. In less dense environments, galaxies have more freedom. They can hold onto their gas longer, continue forming stars, and evolve more gradually. The cosmic web is not just a backdrop for galaxies, it is a force that shapes them. Webb is observing galaxies in different environments and at different cosmic epochs to untangle these effects. How do cluster galaxies differ from field galaxies at high redshift? When did environment start to matter? These are questions Webb can help answer. Let me also say a word about the importance of surveys. Many of Webb's biggest discoveries come from systematic surveys that observe large areas of the sky in a standardized way. Programs like JADIS, Cosmos Web, and others are building databases of thousands of galaxies, each one measured and catalogued. These databases are invaluable. They allow statistical analyses that individual observations cannot support. How many galaxies are there at redshift 8? How does their average luminosity change with redshift? What fraction have active black holes? These questions require large samples, and surveys provide them. Survey data is often made public after a short proprietary period, allowing astronomers around the world to use it for their own research. This open approach accelerates discovery. Different teams can look at the same data from different angles, finding things that the original observers might have missed. Science works best when it is collaborative and open. Webb embodies this ideal. Its data flows to researchers everywhere, fueling a global enterprise of discovery. The telescope is a shared resource, owned by no one country but serving all of humanity. It was funded by American, European, and Canadian taxpayers, built by engineers and scientists from around the world, and operated for the benefit of the entire astronomical community. This is how big science should work. So as we conclude this journey through the cosmos, remember that Webb is not just a machine. It is a symbol of what humans can achieve when we work together toward a common goal, a symbol of our endless curiosity about the universe we inhabit, a symbol of the hope that understanding rather than ignorance will guide our future. The universe is vast beyond measure. It is old beyond counting. It is complex beyond imagination, but it is also knowable. Through patience and effort and ingenuity, we can learn its secrets. We can trace its history. We can map its structures and measure its properties. Webb is helping us do that. Every observation brings us closer to understanding. Every discovery reveals new wonders. Every question answered opens 10 more. This is the scientific enterprise. This is the adventure of discovery, and you are part of it. So keep wondering, keep questioning, keep looking up at the night sky and asking what those points of light really are. The answers are out there, waiting to be found, and Webb is leading the way. The night sky has always been a source of wonder. Long before telescopes, humans looked up and asked questions. What are the stars? Why do they move across the heavens? What is our place among them in this vast darkness? Those questions drove the development of astronomy, from ancient star charts carved in stone to modern space telescopes floating in the void. Each generation built on the work of the ones before, adding new knowledge, pushing the boundaries of understanding. We stand at the latest frontier of that journey. The questions we ask today would have been unimaginable to our ancestors, but they are continuations of the same impulse, the desire to know, the need to understand what surrounds us. Webb represents the current peak of that impulse. It sees farther, clearer, and deeper than anything before, and it shows us that the universe is even grander than we dared to imagine. In our most ambitious dreams, the true scale of the universe is not something we can fully grasp. Our minds evolved to understand the savannah, not the cosmos. Billions of light years, trillions of galaxies, septillions of stars spread across the void. These are abstractions. But we can feel the wonder. We can stand beneath the stars and know that each point of light is a sun, possibly surrounded by worlds, part of a vast cosmic dance unfolding for nearly 14 billion years. That feeling is what matters. The sense of connection to something larger than ourselves. The humility of knowing how small we are, and the pride of knowing how much we have learned despite our smallness. Webb is expanding that feeling. It is adding new chapters to the story, new reasons for wonder and reflection. It is showing us the universe as we have never seen it before. And in doing so, it is showing us ourselves. Our curiosity, our capacity to ask questions across billions of miles and billions of years of cosmic time. That is the true scale Webb reveals. Not just the size of the universe, but the incredible size of the human spirit that dares to explore it. The cosmos is infinite, or near enough. But so too, in its own remarkable way, is human curiosity.